So, for the other part of the modified Atwood machine lab where we're finding mu, let's start with a free body diagram for that one. Notice everything starts with a free body diagram. This should become commonplace, right? So once again, I have M1G, that weight pulling to the right in my example, and we'll say to the right is positive. And I have M2G pulling against it. But I also have friction in this lab. In this setup, we were working on a wooden board with a block of some kind, nothing on wheels or anything. So friction was an issue. And since the whole thing was moving to the right in this case, friction would then be to this side. Force of kinetic friction. Now I want to make sure I am not trying to indicate here that we're in equilibrium. So let me just make sure that that is abundantly clear. That even in spite of friction, right, M1G is winning and we're accelerating to the right. We're not in a state of equilibrium. Okay. And by the way, if we hung the mass and it was just sitting there, it wouldn't even be kinetic friction, correct? It would be static friction. It could be in equilibrium. If we poked it and it started moving and moved at constant velocity, it would be in equilibrium. But in this case, it's definitely not. So I have the following. I have net force equals, once again, total mass, correct? M1 plus M2 plus M3 times N. I also have net force is equal to M1G minus M2G minus force of kinetic friction. Let's just write it for what it is. It is going to be mu kinetic times normal force. But this is the normal force on what block? Block 3 only. Right? The one in the middle. Because it's the only one that has friction. This block that was sitting on the ramp. The other two on either side, the weight's there, the mass is there, just hanging in space. Let's pause for a second then. What do we know about the normal force? So now we're just going to pause and look at block. In fact, here I will use modern technology. We'll go to a different color. We're just going to look at block 3 for a second. What would a free body diagram on block 3 look like? Well, you'd have M3G pulling down, and equal to it would be its normal force, correct? And you'd have the tension caused by block 1, and the tension by block 2, and the friction, all acting on block 3. But what I'm most interested in here is this. Vertically speaking, that block is in equilibrium. To the left and right, all hell's breaking loose and it's accelerating, right? But vertically, this and this are the same, right? So the normal force in magnitude is equal to M3G. Okay, so that was our little aside for a second. So based on what we just talked about, what can I write here? Don't be afraid to say M3G. Okay, I'm talking to my 4th period class who's vaguely listening to me because they know they can just watch it at home later. Okay. I found out what throwing shade means just a couple weeks ago. It's about the same time that I found out about Harambe. I didn't. Really? A whole forest of shade. That's what you're saying I'm throwing.
Not just a tree. Not just a
For the record, on the video, I want you to scroll back and just check to see. Did anybody respond to me when I said, hey, what's the normal force equal to? And you heard practically hear the lights humming in the background, I bet. So, for the record,
I signed the contract saying I couldn't speak.
Okay.
But now
That's true. I did say you couldn't speak. Then as soon as I made the comment, I got all kinds of, Mr. Wellborn's throwing shade. And notice I use ing, throwing shade, because I'm old and that's what I said. I'm not throwing shade. Okay, so here we go. We have M1G minus M2G minus mu kinetic M3G. So not all of M3G's weight is involved here, just whatever friction it allows us to use, so to speak. And we are after, algebraically, we're after that, right? That's our goal. So we're going to go through all the wonderful algebra to get that. So I can write M1 plus M2 plus M3 times A equals. Now on the other side I got, you know what? Yeah, we'll try that. M1G minus M2G minus mu kinetic M3G. I'm going to add, subtract this from both sides, and at the same time add this to both sides. So I'm going to end up with, I'm going to put the A up front, M1 plus M2 plus M3 plus M2G minus M1G equals negative mu kinetic M3G. I don't want to deal with this negative here. So I'm going to change everybody's sign. Now you got to pay attention because I'm also going to change where they go in the order because it sort of looks nicer. So for example, if I change everybody's sign, this is going to be positive, right? So I'm going to put it first. These other two, here and here, are going to be negative when I change everybody's sign. So I'm going to write minus M2G minus A times M1 plus M2 plus M3 equals mu kinetic M3G. So all I did is I multiplied everything there by negative 1 to get rid of this negative sign. So now I'm going to divide by M3G. So I'm going to have M1G minus M2G minus A, all that, all divided by M3G. And so now, what I'll do, once again I'll show you how to do this on Excel, but for each trial, I'm going to take my M1, M2, M3, and A and do this to them, and that will be mu. So I'll probably on my spreadsheet, I'll have M1, M2, M3, and then I'll probably do it in stages. We'll sort that out. But the point is that we're going to perform this calculation for every trial. And every time we do it, we're going to get a new value for mu that are hopefully all relatively close. If your data is like mine the first time around, they're all point something, but they're not necessarily really close to each other, right? Well, here I can show you the end result. Like for my mu, I had this. You can see I had 0.038, 0.117, 0.05, 0.03, 0.1, 0.15. The average comes out to be 0.09 roughly, but notice the standard deviation is 0.04. So it's like 50% either way. It can be anywhere between 0.13 and 0.4 or 0.5. So it's quite a wide range in the data I had. I'd like to do this one again with a lot more data to see if I get something more consistent. So this is a little bit sloppier. I suspect, by the way, here's my end result with the other. I'll show you how to do this on a video. For my best fit line way of doing it, here's my equation in the upper right-hand corner, and it came out to be 9.89. I like seeing 9.8. That makes me feel better. Finding G, when I did that whole line thing I mentioned in the other video, it came out pretty well. But we'll go through in another video how to do this on Excel.